what is matter? What makes up all of the stuff around us? You probably have a lot of ideas about what that is, but for today we're going to introduce that, and this will be a little bit of an introductory course into chemistry also. So the reason that we have to talk about that is because our next chapter here, chapter 2, is on minerals. So minerals are what make up Earth's crust. There are thousands and thousands of different minerals, and minerals together form rocks too, which is the rest of Earth's crust. So in order to understand how minerals work, because they take on very specific shapes and patterns, they have specific chemical formulas. So we need to introduce the nature in which materials bond, what atoms and elements are, isotopes as well. So all of this stuff we'll need to get out of the way. All right. So element is just one type of atom, such as gold or oxygen. And compounds are made of two different elements, like water or steel. So the deal with an element is you cannot break it down into simpler form. If you have a 1 kilogram bar of gold, you cannot reduce that any simpler than that. It's just one type of atom throughout that entire thing, gold. Whereas water, no matter if you have one drop of water or an entire ocean's worth, that's still water, but water is a compound. It's made of hydrogen and oxygen. So theoretically, we could separate the hydrogen from the oxygen, and then we would have two very, very different materials there. No matter what the case, a compound is very different from the individual atoms that make it up. If we just take water, for example, hydrogen gas is odorless and colorless. You can't see it, and it's incredibly flammable. Probably heard of the Hindenburg, a giant airship, a Zeppelin that burst into flames sometime in the 20s or 30s. That was filled with hydrogen gas, and that's part of why it burned so incredibly hot and bright and so quickly. Oxygen gas, well, that's another odorless, colorless gas. We breathe it. Oxygen gas is also incredibly flammable. I think they're called acetylene torches. They use oxygen in that flame. So together, or separately I should say, hydrogen and oxygen are both flammable gases, but when they combine chemically, they become water, which is sort of the opposite of flammable, and it's not a gas, at least not at normal temperatures here on Earth. So, element again, cannot break it down into simpler substances. No matter how much or how little of an element you have, its physical and chemical properties will always be the exact same. That's why if you take like a wire, a copper wire, in a telephone pole, they're really, really incredibly thick. But in a computer or a cell phone, those wires might be incredibly thin, but they behave the exact same way. They transmit electricity pretty much exactly the same. It doesn't exactly matter how thick or thin that wire is. It will have that same property. Its color will never change no matter how much or how little of it, anything like that. So on the periodic table or in nature, there are 92 naturally occurring elements. The elements are created in the core of stars, and uranium is element number 92 on the periodic table. That is the heaviest possible element that can be created and just sort of exist out in the universe on its own. But in labs, we're able to make our own synthetic elements. They have weird names like not americium, but einsteinium, and things like that. And they generally, a lot of them only exist for maybe a few nanoseconds, and then they break down. The first ever synthetic element that we created was plutonium. Plutonium is, you take uranium and you enrich it. You have to add protons to it, and it becomes plutonium. All right. The periodic table, which we'll take a look at, hopefully you've seen it before. There's a method to the way the atoms are arranged, or the elements are arranged. They're arranged by certain chemical properties that they share. And in nature, we find things pretty much exclusively in compound form. You will never run across just pure elemental matter. The only place where you really do is in the atmosphere. About 99% of our atmosphere is nitrogen gas and oxygen gas. Now those are in their elemental form, they're pure. The nitrogen atoms are bonded to other nitrogen atoms, so we say it's N2. But remember, it doesn't matter if you have just one atom of the element or 100 billion atoms of that element, it will behave the exact same way. So nitrogen and oxygen gas. Oxygen is also O2 in the atmosphere. Those are really the only places on Earth where you can find just pure matter. So horizontal rows on the periodic table are called the periods, and there's really no pattern that emerges from there. That's just what we call them. But the vertical columns, those we call groups. And if an element is in the same group, they share a chemical property in the way that they bond with other atoms. So if we take this group right here, group 8, we have oxygen, sulfur, I think that's selenium. I can't remember what that is. This is polonium. What these all have in common is they have two bonding sites. So why is water H2O? Let's just write that down. What does that mean? Well, it means that there are two hydrogen atoms bonded to one oxygen atom. So we could write H2O1, but generally we don't do that. So water forms that way because the oxygen has two bonding sites, so it can accept two hydrogens. Sulfur is capable of the exact same thing. So you could have H2S as well. You could have H2SE, H2TE. What you could not have is H2Cl. That's impossible. You cannot bond two hydrogen atoms to a chlorine atom. You can only bond one. Similarly, if we look at nitrogen, you can't get H2N. That just doesn't happen. You could have H3N because elements in this group will have three bonding sites to them. So you could have H3N, H3P, H3AS, so on and so on. If we look at Earth's crust, now a couple lectures ago, we tried to look at what is the composition of Earth's crust of the Earth in total, and we saw that iron was the most common element, and it's about 35% of the Earth. Well, if we just look at the crust, because this is the part of Earth we interact with and we will study in most of the time, what we see is oxygen makes up about half of Earth's crust. Now again, it's not elemental oxygen, it's oxygen bonded to other atoms. And then silicon makes up about 25%, so 3/4 of the Earth's crust are just those two things. Then we have aluminum, iron, calcium, sodium, yada, yada, yada. So, an atom. An atom is the smallest particle of matter that contains the characteristics of that element. So, why does oxygen accept two hydrogens? Well, it goes back to what I was talking about. It has two bonding sites, and that is determined in the individual atom of the element. The periodic table of the elements is kind of like the periodic table of the atoms. Each element is one specific kind of atom, but we can just make those bigger or smaller. So in an atom, you have the nucleus. That is where the positively charged protons and the neutrally charged neutrons hang out. The electrons, which are negatively charged, orbit around the nucleus, and they're attracted to the nucleus by the opposing charge. It's like magnetism. It's called the electromagnetic force. So here's just a classical model of an atom. You can see here's the nucleus, and there are the electrons sort of orbiting around it. All atoms have just those same three basic parts to it. In their nucleus, they have protons and neutrons, and then electrons on the outside. The only thing that makes one atom different from the other are just the numbers of those things. And it's actually just the number of protons. If you take an atom like gold here, it has 79 protons, so it usually also has 79 electrons. A few more neutrons in that, though. But if we took gold, and if we added a proton to the nucleus of it, it would turn into a totally different element. In that case, it would turn into mercury. If we added an electron to it, it would still be gold. If we added a neutron to it, it would still be gold. But the proton, that one is picky. So protons and neutrons in that nucleus have approximately the same mass. They weigh virtually the same. So we have what's called the mass number. The density of an element, how heavy it is, that is basically determined by the size of its nucleus. So oxygen, it's a gas, it's very incredibly light, and just floats around. Well, its nucleus only has 16 subatomic particles, 8 protons and 8 neutrons. Whereas you take iron, iron is very heavy, well, it has 29 of each of those things. So it's more dense, it's heavier. The atomic number, that is just the number of protons an atom contains. And that one is special because, like I said before, each element can have only exactly one atomic number. The atomic number of gold is 79, and that does not change. You cannot add a proton to it. That would make its atomic number 80, and now it would be the element mercury. However, we could dump extra neutrons into a gold atom or remove neutrons from a gold atom, and it would still remain gold. It would have the same atomic number because we didn't mess with the protons, but it would now have a new mass number. We'll expand on that a little bit more in a little bit. But electrons, they are really incredibly tiny. They're only about 1/2000th the mass of a proton or a neutron. And they orbit around the nucleus of the atom in different levels. In the pictures, you could see there were multiple rings around some of those atoms. Those are the energy levels. If you've taken chemistry, you probably know about those. We're not going to get into the real big detail there. But the electrons are important because how two atoms or elements bond together, that is accomplished through the electrons, and the electrons only. So the nuclei of two atoms never touch each other. Only in places like the core of a star can that kind of thing happen. So it's all down to the overlap, the share of electrons. And here we go. So if you could imagine these two atoms bonding together, which they probably wouldn't, they would only overlap in the very, very outermost layer of these electrons. So not only do only the electrons bond, but only the very, very outermost layer of those electrons. So these electrons inside here or inside here cannot interact with each other in a chemical bond. So here we just see a different example of a bond, a molecule. This is what methane gas looks like. Carbon has 4 bonding sites, so it can accept 4 hydrogens. If it only had 2 hydrogens, it would not be satisfied with that, so it would wait until 2 more bonded to it, you could say. Okay, so isotopes. So we went over, you can only have the number of protons in each element is a fixed number. You cannot change that, but you could, in nature, there can be varying numbers of neutrons. So when that happens, we call that element an isotope. It's like a different flavor, a different version of the same element, and they're just heavier or lighter versions. If you would dump a few extra neutrons into an oxygen atom, it would be an isotope of oxygen. It would still have, so we would just change the mass number. It would become a little bit heavier or a little bit lighter. But in general, their chemical properties are still virtually identical across the board. In some cases, though, some elements have radioactive isotopes. So radioactivity is a process where the nucleus breaks down And as the nucleus breaks down, it loses protons as well in the process. So things that are radioactive actually turn into different elements over time. You probably had heard or know that uranium is radioactive. Well, what does that mean? Well, it means over incredibly long time spans, uranium, if you had a chunk of pure radioactive uranium, if you waited billions of years, that chunk of uranium would eventually turn into lead. That's what a certain isotope of uranium converts into over time. It's lead. So it would turn into something else entirely. So for the most part, we just, the naming of isotopes is, well, we'll get to it. For hydrogen, they actually have different names, but we're not going to look at that too closely. For others, we simply name them by what its mass number is. So if I tell you carbon, I'm just talking about carbon, regular standard carbon. Well, carbon always has 6 protons, as we can see here. So unless I specify, when I say carbon, I'm talking about a carbon that also has 6 neutrons, the matching number of neutrons. If I say carbon 14, I'm talking about an isotope. So 6 plus 6 is 12. 14, we got to jump up 2. So that means I'm talking about a particular isotope that has 2 extra neutrons, which is 8 in that case. So why is virtually all the matter that we see in nature in compound form? Why is it not purely elemental? Well, the reason is because the vast majority of elements all on their own are unstable. Almost all of them have open bonding sites, so they will just naturally grab onto matter, grab onto elements to fill those bonding sites, and that's just the nature of it. Do I have a picture of? No, I don't. There is a group of elements that does not have this, and I'll actually backtrack so I can show you. And that would be right here. These are called the noble gases. So helium, neon, argon, krypton, xenon, I think that's radon, and I have no idea what that is. These do not have any available bonding sites. We call those valence electrons, but they don't have a site for that. So a helium atom cannot bond to any other atom. It doesn't have any room for it. It can't even bond to itself. So the helium gas, like inside of a balloon or whatever, if you could look at each individual atom, you would see that they're all on their own, and they cannot interact with each other. Same with all of these in this group. They cannot bond to anything. We say that they're inert. Okay, back to where we were. Okay, so in order to bond, like we said, it's the electron. So atoms will gain, share, or lose electrons in order to satisfy those bonding sites. So what determines how and if atoms bond together? So if we look at, we draw an atom here real quick. Let's say this is the nucleus, and it has 1, 2, 3, 4. So here's its first energy level. In the first energy level, there are always 2 electrons. And then after that, there want to be 8. So I got to draw a couple extra here. We'll just do that. So here's the second energy level. And I have 1, 2, 3, 4 electrons in there. So that means this wants to fill up and have 8. So it has 4 bonding sites. This is exactly what carbon is like, and all the other atoms in that same group as carbon. So because there are 6 electrons here, we'll assume that there's 6 protons too. That's really what makes it carbon. So carbon, if you remember the picture earlier, it had 4 hydrogens bonded to it. Well, if we add a hydrogen there, there's its electron, a hydrogen there, there's its electron, another one here, and you might not be able to see this one, but another one there. Now we have 1, 2, 3, 4, 5, 6, 7, 8 electrons in that outer layer. So it cannot accept a 9th, and if it only had it can't accept a fifth hydrogen and have 9 electrons out here. If it only accepted 3, it wouldn't be happy yet. It would go find another hydrogen or some other atom to fill that spot. So yeah, it's always 8. We're looking for 8. And so what happens with these electrons is different in the different types of chemical bonds. Sometimes the electron is taken away from hydrogen. Sometimes it's just shared. But that's how we end up with our rule of 8, we can call it. So the electrons that do that, the electrons that are used in chemical bonding, are called valence electrons. Now, in this example, the electrons in this inner layer, those are not valence electrons. They're not used in the bonding process. Only the electrons outside here are valence electrons. So these are what are called electron dot diagrams. Sorry, I'm trying to fix my lighting here. This is called an electron dot diagram, and what it shows you is how many valence electrons different elements in different groups have. So if we, let's go back to water, H2O. So here's oxygen. Its outermost layer, this is not showing you how many total electrons it has, just its valence electrons. So oxygen has 1, 2, 3, 4, 5, 6 valence electrons. Okay, well, it wants to fill that up with 8. So if we look at hydrogen, it has exactly 1. So if we bring a hydrogen over here, we fill that spot, now we're at 7. We bring another hydrogen in, boom, we have H2O. For fluorine and chlorine, they only have 1 available spot. So that's why there's no such thing as H2Cl. There is HCl, that's hydrochloric acid, for example. If we look at this group over here, we can see that they have 8. They're already filled. That's why they're inert and they can't bond with anything else. No, can we pick another example? No, we'll just move on from this. That's just the same thing shown in a different way. So this is what regular table salt is, sodium chloride. Here's your sodium atom, here's your chlorine atom. So if we look at chlorine and sodium, let's look at the outermost layer. So here's 1, 2, 3, 4, 5, 6, 7. So chlorine needs an extra electron. Well, sodium can give it to it. And if we do go back here, here's sodium with its 1 available electron. Here's chlorine with its missing electron, we could say. So what happens is, in this type of bond, chlorine will actually steal that electron away from sodium. And then if we look here, this outer layer of the sodium atom, it sort of doesn't exist anymore. It goes away. So it defaults back to the layer underneath of it, but we can see 1, 2, 3, 4, 5, 6, 7, 8. It's got the 8 there, so everything's all good. An atom will not jump to the next energy level until the one before it is totally filled with 8 electrons. And there's a methane molecule again. Okay, so the different types of bonds. Now, normally, an atom has an equal number of, we're going to change that because that's not true. Neutrons is not necessarily true, but normally an atom does have equal numbers of protons and electrons. So this makes the charge of the atom neutral, because as we said earlier, the protons are positively charged and neutrons are negatively charged. Sorry, electrons are negatively charged. Neutrons don't have a charge. So if an element has 6 protons, that gives it a +6 charge. If it also has 6 neutrons, that's neutral, so it doesn't do anything. If it has 6 electrons, then that's -6, and we're back to 0. Ta-da. So what happens, though, is, like the example we just saw before, if an electron is lost or gained during chemical bonding, now the atom has a mismatch of positive and negative particles. So we say that it has become an ion. And that just means a charged atom. It doesn't mean positively charged or negatively charged. It means both. If you want to get specific, I believe positively charged ions are called cations, and negatively charged ions are called anions. I think that's what it is. So here is sodium, the sodium chloride ionic bond again. So here they are before they bond. And we don't see the nucleus, but in chlorine the nucleus has 17 protons. That's its atomic number. And in sodium it has 11 protons. That's its atomic number. So here, before anything has happened, their overall charge is 0 because there's 17 protons and electrons in chlorine and 11 of each in the sodium. Chlorine has that one available spot, and sodium has just, if it could just get rid of that one outer electron, then it would go back to the layer underneath of it where it already has 8. So that's what they do, but now, if it does that, sodium hasn't gained or lost any protons, so it's positively charged. It has 11 protons and only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. Chlorine, it gained an electron, so it's negatively charged. That's an ionic bond. Bonds that occur between two charged atoms. So that electron will stay on the chlorine side for forever until you melt the things or found some way to separate them from each other. Now the sodium and the chlorine atoms are locked together after their bond. You cannot pull them apart unless you the way to separate bonds is to get a material to its melting point. So you think of water, you can separate all the water molecules from each other with if you melt something, then you can pull them apart. Otherwise, they're solid. Ionic bonds are really incredibly strong because of that electromagnetic force. Compounds that are ionically bonded have incredibly high melting points. Regular table salt, if you would pour some table salt onto a pan, throw it on your stovetop, crank the burner on high, and leave it there for an hour, the salt would not change. It would get hot, but it would not change color. It would not start to melt or do anything because it's ionically bonded. The melting point of salt, I think, is something like 1800 degrees Celsius. So that'd be 3000 degrees Fahrenheit or so. Really, really incredibly high. We took sugar. Sugar looks just like salt. Pour that on a pan, put on your stove, put on high. That will start to melt fairly quickly because it's not ionically bonded. I'm going to skip this video for now. Okay, so covalent bonds. In these bonds, rather than the electron being permanently transferred over to one atom, in this one, the electron weaves back and forth between one atom and the other. It's shared. So the valence electron freely orbits from one atom to the other. And covalent bonds are much weaker. That is what sugar is held together by, a covalent bond. Sugar is a much more complicated molecule. One single molecule of or compound of salt is one sodium atom, one chlorine atom. Well, to form sugar, you need 24 total atoms. It's 6 carbons, 12 hydrogens, and 6 oxygens, all bonded together. So it's a much bigger molecule, but all those atoms are much more loosely held together, so melting points are really low. Life is based on compounds that are covalently bonded together. So when I eat foods, like the proteins and the carbohydrates is just another word for sugar. My digestive system and inside my cells, it can break apart those molecules and reassemble them pretty easily because the bonds are fairly weak. Now, there is some energy involved in that. That's why mammals are warm-blooded, because of all the tricky metabolic activities going on with that. But ionic bonds, our cells, biology has not figured out a way to do that because the energy it takes to separate those ionic bonds is incredibly high. In order for my body to be able to break apart ionic bonds, my internal temperature would be thousands of degrees rather than just about 100 degrees Fahrenheit. So, good for that. Technically, a molecule is two or more atoms covalently bonded. So water is a molecule because the hydrogen and the oxygen share the electron. Glucose, sugar, is a molecule, but salt is not technically a molecule. So I think I said that earlier. Technically, that was incorrect. So here's a GIF that just kind of shows what a covalent bond is like. If you get two hydrogen atoms, they will bond to each other, but the electrons, both of them, weave back and forth. If we looked at a more complicated molecule like sugar, we would see all 24 atoms passing back and forth their electrons. And I don't have a GIF of that. Here would be two nitrogen atoms. No, not nitrogen. Nitrogen atoms bonding together. They do the same sort of thing. And that's the end.